hydrogen. You hear about it all the time, right? It's supposed to be the clean, green fuel of the future. Powerful, zero emissions, basically the perfect solution. But what if its greatest strength is hiding a pretty terrifying secret? Well, that's exactly what we're digging into today. Okay, so let's just lay it all out. On one side, you've got the promise, this amazing fuel that could literally power a sustainable world. But on the other side, there's a serious peril. New research is showing that when you're talking about liquid hydrogen in a confined space, think a tunnel, the risk of a catastrophic explosion is very, very real. It's this exact paradox we're going to unpack. So what is this stuff really? We're talking about liquid hydrogen, or LH2. To get it, you have to cool hydrogen gas down to a cryogenic temperature. We're talking minus 253 degrees Celsius. Unbelievably cold. This turns it into a liquid, which makes it incredibly dense with energy. And that's fantastic for things like trucks and ships. But it also means that if you have a leak, you're releasing a massive amount of fuel, which makes it way more dangerous than a leak of just regular gaseous hydrogen.
And this is where things get really hairy. Tunnels. Their enclosed design is like the perfect trap. It can contain all that leaking fuel, which can dramatically amplify the force of any blast and, make any rescue attempt almost impossible. And with the first liquid hydrogen-powered trucks already hitting the roads, this isn't some far-off theoretical problem. This is a real-world risk we have to get our heads around, and fast.
So to figure out just how big this risk is, scientists at Curtin University ran this fascinating and, frankly, terrifying simulation. They built a digital model of a 40-kilogram liquid hydrogen tank rupturing inside a highway tunnel. So let's walk through exactly what they found, step by step. And here it is. This is the digital twin of the 200-meter tunnel they used. You can see the ruptured tank right there in the middle. The scientists basically put virtual sensors all over this place to track exactly what happens to the gas, the pressure, and the temperature down to the millisecond. Now, here's what's so wild about how a liquid hydrogen leak behaves. It's completely counterintuitive. I mean, you'd think a gas that's famous for being lighter than air would just shoot straight up and disappear, right? Well, you'd be wrong. The simulation shows 3 very distinct and very dangerous stages. And this right here shows that first crucial stage. Because the leaked liquid hydrogen is so incredibly cold, the gas cloud it forms is actually way denser than the air around it. So what does it do? It sinks. It literally hugs the floor of the tunnel and spreads out sideways, creating this wide, low-lying, and highly flammable zone. Okay, so what happens next? As that super cold gas touches the warmer air and road, it starts to warm up, expand, and rise. But it's not neat and tidy. As you can see, it fills up the middle of the tunnel in this chaotic, messy shape, mixing with oxygen and getting more and more volatile by the second. And finally, in stage 3, the cloud has warmed up enough that it starts acting like the hydrogen we're more used to. It rises up and sticks to the ceiling of the tunnel. Get this. In just 40 seconds, the simulation shows the entire space goes from being totally safe to being filled with a massive, invisible, explosive cloud, just waiting for a spark. So now you've got a tunnel just primed for disaster. All it would take is one tiny thing, a spark from scraping metal, an electrical short, anything. Let's take a look at what the simulation shows happens in that exact moment of ignition. 50 bar. That is the peak pressure the simulation recorded. To put that in perspective for you, that's over 725 pounds per square inch. It is a level of force that's hard to even wrap your head around, capable of absolutely obliterating vehicles and tearing the tunnel structure apart. And this is what that pressure looks like. See, it's not just a fire. The explosion's shockwaves slam into the tunnel walls, bounce off, and then crash into other waves. It's a process called superposition, where the waves basically stack on top of each other, making the pressure more and more intense. The tunnel's own shape actually turns it into a weapon. And with that insane pressure comes unbelievable heat. We're talking 2,500 degrees Celsius. That's hotter than molten lava. It's more than hot enough to melt steel and cause the tunnel's concrete lining to fail catastrophically. So here's the absolute kicker, and I'm quoting the researchers directly here. The explosion overpressure resembles a detonation more akin to a TNT explosion. See, a normal fire just burns through fuel. That's a deflagration. A detonation is totally different. It's a supersonic shockwave that obliterates everything. It's the difference between a fire and a bomb. Okay, so That was all pretty grim. But the point of this research wasn't just to freak everyone out. It was to find solutions. The scientists also simulated a couple of ways we might be able to prevent this disaster, or at least make it a lot less severe.
And wow, the results are just stunning. Just look at the difference here. On the left, that's the massive flammable cloud we saw before in a regular tunnel. On the right, that's what happens when you have a suction ventilation system running. It is a night and day difference. The ventilation just pulls that dangerous hydrogen right out of the air, shrinking the potential fuel for an explosion.
And the hard data on this slide tells the story even better. Let's look at this. The baseline pressure is a terrifying 54 bar. Now check out that second line. Just by making sure the air has high humidity, you cut that pressure by more than half, down to 26 bar. And with the suction ventilation, it drops all the way to 22 bar. That's a 59% reduction in explosive force. That is a huge, huge improvement in safety.
So how do these pretty simple ideas have such a huge effect? Well, it all comes down to some really elegant physics. When the air is humid, the water vapor in it soaks up a ton of heat. It's like a fire blanket on a molecular level, and it slows the whole explosion down. The suction ventilation is even simpler. It just sucks the fuel right out of the air. Less hydrogen means a smaller boom. And these aren't some sci-fi technologies. They're things we can do right now. So, what's the big picture here? What does this all mean? This research is basically a critical science-based roadmap for how we can build a safer, hydrogen-powered future. Let's just quickly sum up the key takeaways. Look, the bottom line is that while liquid hydrogen is an amazing tool, the way it behaves in places like tunnels means we need a totally new safety playbook. The fact that it sinks first changes everything, where you put sensors, how you plan evacuations, and yeah, the explosive potential is massive, but this research proves we already have the tools to manage that risk. This isn't about stopping progress, it's about being smart and building our clean energy infrastructure safely from day one. Which leaves us with this one final crucial question. The hydrogen economy is coming and it holds so much promise. But as we race to build that future, research like this is a powerful reminder that we have to ask the hard questions. Are we just building it fast, or are we taking the time to build it right?